Today we will be having Michael Barz speak about EN algebras.
Yeah, so the first half of this talk is going to be mostly like kind of general formalism, and then the second half of the talk, oh wow, shots. The second half of the talk is where we'll talk about things actually related to this sort of Kamikawa number story. So I think it was 2 weeks ago, Justin sort of gave a talk and he defined like infinity-operads and stuff of that nature for us. And so today's talk is going to be about a very particular type of operad called the EM algebra. But I wanted to sort of go over again a little bit what operads are, but maybe from a different perspective. So I think Justin gave like a very kind of higher categorical and like sort of framework independent way of doing things. I prefer to think of infinity categories as topologically enriched categories. And so I'm going to define operads as a certain type of topologically enriched thing. So sort of the very first operad that Justin had defined for us was this thing called a SIPS. And this is the operad with the property that like algebras over it are just associative algebras. And I want to talk a little bit about sort of the intuition behind that, because this is Peter May's school, and so maybe he would want us to like draw a little commutativity and things like that. So if I have some sort of space X, and maybe it's a base space. So this is just a topological space with a base point. I can form its loop space, omega X, which is just like the space will maps from the interval into X, sending 0 and 1 to this little base point. So this is like loops, and I can give this the compact open topology to make this like a nice topological space. And sort of as Poincare first noticed, there's a natural multiplication operation on this. Namely, I can sort of concatenate loops. But there's kind of like a problem, and this is the problem that Poincare had to solve when defining the fundamental group, which is that concatenation is not like literally on the nodes an associative operation. It's only sort of associative up to home. And we're going to revisit this example in a lot more detail later, but for just this operad, I want to talk a little bit about this sort of Peter May-esque setup for talking about homotopy associative things. And these are what are called the sort of AN operats, which come right before the EN operats. So if I have a topological space, maybe I'll call it X, maybe I'll call it S. If I have a topological space S, and I have some sort of multiplication on it, I might ask when this multiplication sort of makes S into like a homotopy group. And so, or I guess even a homotopy model. This operad is really for models. So the sort of strictest axiom you could demand is that mu is literally sort of an associative multiplication. This is like the strictest possible thing. But even on that loop space, concatenation of loops is not literally an associative operation. So instead, people kind of weaken it. And instead, really, they say there's sort of a homotopy, aka a path in S, from A times B times C to A times B times C. So we say that these two things, there should be a path between them in S. Like we should think that these two products are on the top. And we should think that we have some sort of nice way of building paths between like two different associated products like this. And this is sort of like the first level of homotopy associativity you can ask for. But you might also ask for sort of higher associativity. And so if I have like 4 terms, A, B, C, and D, that I want to multiply together, I can sort of group them in a lot of different ways. You do something like this. You do something like this. Do something like this. So there are many, many different ways of grouping them. I think 5 in total if I were to draw them all out. And somehow they should all be the same. Except when I just have like this sort of one sort of association relation, and I want all 5 of these to be the same, a certain type of problem happens. So if I take this like AB times CD type thing and sort of do this type of regrouping, then I see that there's some sort of homotopy between this product and this product. And if I do sort of that type of regrouping again, maybe sort of the other way, then I can sort of construct some homotopy between these two products. And I can kind of go around in a little bit of a pentagon. So I can sort of regroup this type of associativity and regroup this product like that, A, B, C, D, and hopefully these will sort of converge in the exact same thing. Which, what do I want it to be? A, C, D. There's some fifth way of grouping them that I'm not seeing. Somehow, whatever the fifth way of grouping them is, I should put it there.
Somehow would be you bracket BC and then you bracket A. We have an answer from Zoom too, yeah. Everyone's told that at the same time.
Okay,
Yeah.
there we go.
It's just a pass around the postgres.
Great, so we get this little sort of pentagon of different ways of associating. And in particular, if I start here and want to get here, there's two sort of paths I could take. I could take this way around the pentagon, or that way around the pentagon. And those are two different sort of associations witnessing that these two are the same product. So an even like higher level of coherence that I could have in my associativity is that I demand a homotopy between this path and that path in S. And you can imagine, like, so I struggle to draw this pentagon, so I'd probably struggle even harder if I tried to draw like a three-dimensional thing that happens if you're trying to group like 5 terms together. So I'm going to stop drawing at this point. But this is sort of the idea behind these AN-operads, which I think refers to Peter May, which is basically, you know, sort of at the beginning levels, you just require some sort of these types of associations, but you want them to become more and more coherent. And so sort of as n increases, you can imagine the more and more coherences that you can imagine, like more and more homotopy coherences are fulfilled. And in the end, it sort of terminates with what people call like an A infinity-operad, or which other people call the operad, which is sort of the most homotopy coherent associativity requirement that you could ever possibly demand. And this omega x, it actually is an isosoperad. So it's sort of multiplication by concatenation. It turns out to be like as homotopy associative as possible.
It's an algebra.
Yeah, sorry. So remember, like, so Justin defined like algebras for an operad inside of a symmetric monoidal infinity category. So spaces is a symmetric monoidal infinity category. So I can speak of a topological space as being like an algebra over an operad by imagining it as sort of an algebra object in the category of spaces. So this sort of leads into the sort of EN algebras that I guess this talk is nominally about. So, and the sort of first claim is that the E1 operad is the same as the isosoperad. And depending on how you do things, you could take that as a definition, but I'm going to define E1 in a slightly different way, for which this will become like a theorem. And so what is the E1 operad? And this came down to sort of, I think this was first defined by Peter May, because he was asking a question, what sort of structure does the multiplication on omega x have? Well, how do I like actually concatenate two paths? The sort of simplest way of doing it is sort of, I do f for like the first half of time, and then I do g for the second half of time. Hopefully those formulas are correct. So I do f for the first half of time, I do f for the second, I do g for the second half of time. But I could also do like other sorts of things. And so what Peter May sort of realized was that I can imagine I have this sort of interval from 0 to 1. And this is sort of the domain of my path. And what Peter sort of found convenient is to just consider the open interval with sort of the convention that, well, we already know where it goes in the bound point. Like 0 and 1 both have to get sent to the base point. So we don't really need to specify what our map is doing there. And then we just look at all the different ways of rectilinearly embedding two disjoint copies of the interval into this interval. And this is like all the different ways you can think of sort of concatenating two paths in this way. And you can imagine like this sort of dead air just means do base point. And these rectilinear embeddings, like here, this corresponds to some sort of rectilinear embedding given by t goes to 2t and t goes to 1 minus 2t. So this sort of is some kind of like filled up interval like that. And so this is sort of what Peter thought was kind of going on. And to encode this, he sort of invented this structure called an operad. And to Johnson's definition, an operad was a certain type of like infinity category fibered over the nerve of this category of like pointed finite sets. And sort of how Peter May kind of classically thought of an operad like that is that for each like integer, 1, 2, 3, etc., I have a different kind of collection of operations of these areas. So like I have some operations that take 1 number as an input, some operations that take 2 numbers as an input, some operations that take 3 things as an input. And the sort of most naive thing one can do is to make like these sets of operations. Like you have a set of 1 input operations, a set of 2 input operations, a set of 3 input operations. But if we want to go into this sort of infinity world, we're going to want these to be sort of topological spaces of operations. So this is sort of the idea that an infinity category is the same thing as a topologically enriched category. And so I can make these sort of topological spaces to get infinity-operads. So what is an operad? Well, it starts with a series of spaces, a series of topological spaces, or sort of an nth space you should think of as the space of like operations that take in n inputs, as well as the following. Oh wait, maybe I should call them x1 to xn because I'm about to draw a symmetric group. So the symmetric group on n letters is going to act on xn, and you should think this is like if I have an operation with n arguments, I can commute the arguments, and so there's somehow there's natural actions of xn. And the second sort of axiom is that I should have some sort of unit operation. So I should have a map point into x1, and the idea is that this is like the identity. Like, so there's some 1 element operation that just takes its argument and outputs that argument. This is sort of what this unit axiom is doing. And the last thing is sort of what really makes an operad, which is the following sort of composition law. So if I have like, so I have some sort of composition maps from xk times x and 1 times x and k mapping into x and 1 plus nk. And so what is this doing? Well, you can imagine if I give you some function of 3 arguments and then I give you some other operations, maybe 1 operation of 2 arguments, 1 operation of 3 arguments, 1 operation of 4 arguments, I can sort of compose these together and get a new sort of very big operation that takes G1 plus G2 plus G3 arguments. So this is sort of what these composition maps do. And there are some sort of coherence axioms that basically say composition is associative, and this sort of identity actually behaves with respect to composition like an identity, and you can probably find them written out on the NCAT lab, but I won't go through like writing them all out because they're kind of messy.
To be clear, this is exactly the definition I gave, right?
Yes.
It's just like you're just writing out what that kind of composition operation on symmetric sequences is explicitly.
Yeah, okay. So this is like exactly sort of what just defined, but I'm giving it like very, very explicit. So like this is what would be written in Peter May's book, right, for example. Yeah, and so this is sort of this is my definition of topology. Oh, yep.
Yeah, stupid question. So does the matter for n log to nk, like, do we need to specify the order on it? It doesn't matter.
Oh, so we do think of this as being an ordered product because you can imagine if f is sort of not really, if f is not like a symmetric operation, like if f of xy is different than f of yx, then you can imagine if I plug in G1 then G2, that might give a different answer than G1 then.
Oh, and
Then
then
G2.
is that where it's from, like going back to this coherence stuff? That's where it's.
Oh yeah. So the associative operad is basically the operad where sort of for the n-arity operations of the sort of associative operad are just the different ways of multiplying n things together. And so that is like that's like a particularly degenerate operad. But most operads sort of the order matters quite a bit.
So it is, to be clear, it's a kind of associative algebra structure in its own right, which is why it's ordered, right?
Yeah.
It's an instance of this actually, but with this like weird composition product on symmetric sequences.
Yeah. So this is sort of this is I guess what I call a topological operad. And in the sort of standard way of converting a topological category to your preferred mode of infinity category, you can view these sort of infinity-operads in Justin's sense. And I think also like, if you just think a lot about what Justin's definition means and just take the view that mappings between objects in infinity categories are the same topological spaces, then this exactly sort of recovers his definition. So, okay, great. So any questions about that sort of story? Okay, yeah, now I can sort of define E1. So E1 is a particular topological operad where, so the Xn space for E1, oh God, okay, there's sort of a collision of letters, so I'm going to start calling this Y. So the Xn space for E1, you should think about it as sort of defining, like different ways of composing n paths. So if I have n total paths, how do I compose them? Well, sort of using this sort of Peter May idea of path composition, we should think Xn, or the E1 operad, is defined as the space of rectilinear embeddings. Maybe I'll call it rect. So rectilinear just means if I write it out in coordinates, it's given by these sort of like affine transformations, like it's made out of scalar multiplications and additions and things like that. Rectilinear embeddings of a sort of disjoint union of n open intervals into the open interval. So this is sort of the E1 operad. This is the E1 operad, sort of defined Peter May's way. So I look at all the rectilinear embeddings of n copies of the unit interval into the unit interval. And this is sort of via formulas of that nature, exactly the same way as all the different ways of concatenating n different paths. And so naturally, omega y sort of is an E1 algebra. So these loop spaces are always E1 algebras. And I mentioned earlier that E1 equals a sus. So now I kind of want to see how we get that. And for this, actually, maybe it's helpful if I define En in general. So the E1 operad is when I sort of look at rectilinear embeddings of n copies of 0, 1 into 0, 1. If I look at the En operad, that's sort of the operad where the nth space is rectilinear embeddings, not of copies of 0, 1, but of copies of 0, 1 to the power of n. So you can think of I as like some finite index set of order n. So I look at now all the different ways of embedding sort of so many copies of 0, 1 to the n into 0, 1 to the n. And these are the different spaces I have there.
Just to clarify, because you have two n's, you have the en, you also have the xn.
Yeah, okay, that's maybe I'll call these like, maybe I'll call this EK algebra. So an EK algebra.
Wow. It's always an index matter.
Larry calls them BK.
Oh, he does? Oh,
Never mind,
then you're on solid
At
ground.
least in the original like DAG papers.
Yeah.
Okay.
So
What is that?
oh, so I is sort of an index set. So being a bit cavalier with notation, I can think of either an operad as a sequence of spaces, one for each natural number, in which case you think of this as like being like the xn space for the EK operad is times 1 through n. But I think some people prefer to think of it as like a functor from finite sets to spaces, in which case like this would be any finite set. But finite sets have isomorphism sort of this, so I can get away with only
This would
telling
be
you
your
the
like
xn.
X and panel.
Yeah, so this is like my xn spaces for the EK operad. So for the E1 operad, for the E1 operad, xn is given by this space, and for the EK operad, xn is given by this space. Where literally the only thing I changed is this, I put like k's in there. So this is like a k-dimensional version of the E1 operad. Great. So now I want to talk about a different way of viewing the EK operads, which makes it more clear why the E1 operad is the same as the sus operad from before. So for this, we have to sort of remember when we're working with infinity categories, model as topological categories. If I sort of have a homotopy equivalence of spaces, I should think of that as like being a genuine isomorphism. Like sort of when I'm working in this infinity categorical world. So there's a map from the configuration space of endpoints in 0, 1. So the configuration space of n points in 0, 1 means I have n distinct points. For me, I'm taking the convention that configurations are of distinct points. So I have n distinct points in 0, 1, and there's a natural map from well, there's maybe a natural map from that space Xn, rectilinear embeddings of n copies of 0, 1 into 0, 1. There's a natural map from Xn into this configuration space. How? Well, if I sort of imagine I have like sort of n little disks embedded in this big disk, I can just take the center of each disk, and that gives me n distinct points. And they're distinct because that's like a disjoint union that I'm rectilinearly embedding. And since it's like an embedding of disjoint things, all these disks ought to be disjoint, which means their centers definitely are distinct.
And just to make sure I'm following that intuitively, the configuration space is defined when they're need to be distinct, is actually disconnected, right? Because you can never swap the order of, say, it's actually more than one connected component.
Yeah, exactly. In fact, I can even draw one.
Yes, it's
Maybe I'll just draw an example. So if I take the configuration space of 2 points in the line, so 2 points in the line is sort of like a rectangle, but I don't allow them to be distinct. And so, well, first of all, it should be an open rectangle since this is the open interval. And then I should also delete the diagonal. So you're exactly right. There's 2 connected components because I can sort of never swap the 2 points. So like this point and this point, the sort of swapped tuples, they will never ever be close. So, they're very sad. So
here the BunG seminar acknowledges the intermediate value theorem. But
exactly. So there's a natural continuous map from Xn into the configuration, and it turns out that this is a homotopy equivalence. And sort of blurry proves this. It's kind of a fun exercise in point set topology. The idea is that you can construct a homotopy inverse for any configuration of n points. Just sort of continuously choose. You have to construct a map backwards. How do you do that? Well, you sort of want to continuously choose a radius. So what you do is you look at like the biggest gap between 2 points, or I guess the smallest gap between 2 points, take half of that, and then that will end up sort of being a continuous way of choosing radii. And that map will be like a homotopy inverse to this map that I just defined. So there's this map from here to here, and it's homotopy equivalence. So I could define a perfectly valid topological operad by saying configuration of n points in 0, 1, and that would be sort of a completely equivalent topological operad to the E1 operad. And similarly, if I want to use the EK operad, I could just change this to a K, and the exact same argument would go through. And so I can view the EK operad in 2 ways. I can view it as its sort of space of n-area operations. It's just rectilinear embeddings of sort of n cubes into 1 cube. Or I could view it as its space of n-area operations is the configuration space of n points.
I know that one, but higher Ks you're going to be able to move past one, right?
Yeah, so it looks like more and more.
Style. Yeah. H higher pies are okay. Yeah.
Exactly. So it looks more and more complicated.
Sorry, just one, I think it's worth pointing out, there's a more even pedestrian explanation for why these spaces are homotopy equivalent, right? In the case K = 1, which is just their connected components are contracted. So it's like, like they're both just like homotopy equivalent to like the symmetric group on. So it's K = 1. But yeah, I mean, this is like related to the question I was asking the other day, which is like, I wonder, it's interesting because when K = 1, you're using these like crazy infinite dimensional spaces to model like a finite discrete set, right?
Yeah.
But then for higher K, like I don't know the way to do it. So,
Yeah, and so maybe great. And so I guess this sort of explanation I just gave is exactly why E1 is equal to the Assoc operad. So the Assoc operad, sort of its space of K-area operations, is basically just permutations of K letters. And well, hey, what's the configuration of K points, or I guess of n points in 0, 1? Well, it's just like the different ways of ordering n points, like at least up to homotopy. So it's just the different ways of ordering n points. And we can even see this with this sort of picture that we drew here. Like this is sort of exactly the observation that Aaron had, that once I've sort of ordered the points, I've fixed the connected component, and then I can never leave that connected. Great. And so this is sort of why, so if you just think like really hard back to that definition of the Assoc operad, then it turns out that its sort of space of K area or of n area operations is precisely a different way of ordering n points. But that's exactly, I guess, homotopy. That's exactly this configuration. Great. And so now we know why E1 equals Assoc. And so now I guess sort of, so the idea is the first half of this talk will sort of get rid of all the EN algebra basics, and in the next half I can talk a little bit about duality things. So the next sort of EN algebra basic thing I want to talk about is Dunn additivity. What is Dunn additivity? That's a good word for this.
So it's relevant.
Oh, Dunn additivity? Yeah, maybe I'll write it down. I will say, like,
There's a poet, Dunn.
Dunn.
I think so, yeah. And Tom, how do you spell Dunn the poet? That'd be so lyric, you would know.
So Dunn additivity. So
Yeah, D-O-N-N-E.
Dunn additivity, we can sort of view it. We can sort of view it in a number of equivalent ways, and I think the sort of first way of saying it that I'll start with is that EK tensor EJ is isomorphic EK plus J. So somehow there's a notion of tensor product of operads, and if I take the tensor of the EK operad and the EJ operad, I get this K plus J operad. So I get this K plus J operad, and this is the idea of Dunn additivity. And Dunn additivity, if you want to like rigorously prove it, it's actually like pretty hard. So instead I'm just going to give a handful of different intuitive explanations of why one should expect Dunn additivity, and then direct you to, I guess, higher algebra if you really want to prove it.
Is this the like Boardman-Vogt tensor product or whatever? Is that something?
Yeah, so this is the same as the Boardman-Vogt tensor product, although I think when I'm using it, I'm using whatever Lurie defines the operad tensor product.
Yeah, I don't know what the, because I like gave several different monoidal structures on symmetric sequences, and I don't actually know what this is like. Maybe it looks fun, but yeah.
Yeah, I think maybe the sort of best explanation I can give, which is a little bit more down to earth, if you don't want to define the tensor product, but want to understand what Dunn additivity is telling you. So remember, if I have a symmetric monoidal infinity category, and I have an operad like EK, I can form a category of EK algebras of that infinity category. So sort of like algebras for that operad. And a sort of equivalent formulation of Dunn additivity, and this is sort of the formulation that will actually be more important to us when we're actually using Dunn additivity, is the following. If I take the EK algebras on the infinity category of EJ algebras, this is naturally isomorphic to the infinity category of EK plus J algebras. So if I start with some infinity category C, and I look at all the EK plus J algebras for it, that's the same as taking the EK algebras of the EJ algebras.
Sorry, so C, what is C here?
C is a symmetric monoidal infinity.
So you're using somehow the EK algebras formed, the tensor product of EK algebras is again an EK algebra, right?
Yes, yes.
Which is not totally clear.
It's not totally clear, but like the tensor, it's also not a hard thing. It basically the EK sort of acts separately on each factor. Like if you want, why don't I actually give a kind of.
I guess I'm just gonna say it's not a totally general thing. If you do this like for an arbitrary operad, that's not true. Like, for example, the tensor product of the algebras is not fully algebra typically, so I just wonder like what it is about. Because it's true for associative algebras, it's true for commutative algebras, but I don't know like what is it about them that makes this work that doesn't work for like a Lie algebra.
Oh yeah, actually that's a good question. So I don't know what particular structure on EN you're using.
Right, for that. Like I'd be totally happy with this if C was like Cartesian symmetric monoidal, but then I don't know what works. Anyway.
Yeah, so maybe what I'll do now is I'll say a little bit about what.
So question from Zoom, how is the tensor product statement related to the compositional statement?
Oh, like how are these two statements related? That's something I don't want to get into, but it basically sort of. When you think about, I guess when you unpack the definition of a tensor product of operads, you'll find that like giving an EK tensor EJ operad sort of structure on an object, like giving an action of this operad on an object, like making an object an algebra for this operad, is the same thing as giving separately an EK and an EJ algebra structures that are compatible in some way. And when you have those sort of two mutual compatibilities, I guess this is sort of what it's encoded. Like I take an EJ algebra, and then I give it an EK algebra.
Like that isomorphism, like K and J both one.
Yeah, so here's what I think I want to look at this one. And first I want to say in a little bit more detail, like a very concrete model of EJ algebras. And then from that model, we can actually kind of explicitly see what this isomorphism is for even arbitrary K and J.
Sorry, can I have one more question?
Oh, yeah.
Just about this tensor product of operads, is there? Does it I don't know the construction, does the construction give you an explicit description of n-ary operations?
There might be some construction that does, but the construction I know does not, but it's also because the construction I know is done by Larry in higher algebra when he's at sort of an infinity categorical level,
Right.
where at least to me, I sort of lose track of this. So it might be that Jacob Larry could sit down and tell you, but I don't know.
I'd be curious if I mean, ideally it would be, in terms of like suspensions, loops and things like that, right? Because, for example, like I don't know a general description of what like the n-ary operations in the EK apparatus, just kind of to be clear. Anyway.
Yeah, so, no, but that's a good question. So I think now what I want to do is talk a little bit more explicitly about how it's actually think about an EK algebra, and then we can see where this isomorphism is coming from. So I want to see a symmetric monoidal commutativity category. And I want to say what it means to give sort of an EN algebra form. So Justin sort of defined algebras as these sorts of like crazy little functors. So what does like this crazy little functor look like here? Well, it should be a functor from a category which Larry calls math U, but math U is kind of hard to draw on a short form, into C. So it should be a functor A from math U into C. What is math U? Well, this is sort of this sort of category of open subsets of 0, 1, I guess if I'm using an EN algebra, 0, 1 to the n, which are homeomorphic to 0, 1 to the n. So this is sort of like disks inside of 0, 1 to the n.
Do you mean disjoint union? Oh, sorry, I see this.
Yeah, no, so I'm not going to impose that disjoint union of 0, 1 to the n's for now, and you'll see where the disjoint unionness, how that is encoded by this. So the idea is sort of
So this is why, in particular, when we're talking about algebraic curves, these are all E2 algebras, because this is right, or
Well, because C
Because
is
C is
two-dimensional
two-dimensional.
over R, yeah.
two-dimensional over right? So yeah, this is,
yeah.
That's
thought for a moment it's
That's where the
completely nonsense. It's like,
that's why it's n equals 2.
yeah.
So, and this functor, we should have some additional data coming from these little compositions, which is that I should have, if I have, well, this is sort of where I encode the disjoint union. So if I have sort of U1, disjoint union up to UK, sort of embedding into a bigger disk V, this should sort of give rise to a map of tensor products, where I take this sort of K-fold tensor product, and it should map into A of B with the property that this map is an equivalence. So this map is an equivalence if K equals 1. So this map should be an equivalence if K equals 1. So in other words, like this A, kind of in some sense, all the objects, like all the sort of objects in the outputs of A are all equivalent in this infinity category C. So I should think I have many, many different equivalent representations of some object of C that sort of has this algebra structure. And then the algebra structure is sort of specified by telling me if I have like a bunch of if I have a disjoint union of disks inside of it, how I sort of multiply them together to get a map like this. So this is sort of the algebra structure, is having these compositions. Yeah, and so this is sort of one kind of very concrete model of algebras of an operator. And so now, if I look at sort of this statement, and I kind of ask myself what it kind of means, one sort of cheap thing to do is I can say, hey, if I have an EK plus J algebra, how can I get an EK and an EJ algebra? This, I'll define a little functor. So say A is some sort of E K plus J algebra in C. What I can do is I can define phi of A, which will be something in C that has both, that has like an EJ, EK algebra structure. And how should it do it? Well, remember, it should be some functor that takes in, so how do I give it like, what should we call it? How do I give it like that sort of dual algebra structure? Well, it should be a functor that takes in an open subset, and then it takes in sort of another open subset. And which open subset should I output? Well, I'll output A of U times V. So sort of what's happening here is phi of A is going to have an EK and an EJ algebra structure. And how does that arise? Well, if I take like a K disk and a J disk, then phi of A is going to be the thing that outputs like A of the product, which is from like K times J disk. So this is some sort of functor between those two categories, and the sort of most explicit version of the claim of non-activity that I know, at least, is that this functor is an equivalence of categories. Great. So let me check how I'm doing on time. So yeah, so this is sort of the idea of Dunn activity, and maybe one sort of more way of thinking about Dunn activity is at the start. I was telling you that these sort of loop spaces, loop Y, they naturally come with an E1 algebra. And now we can imagine loop space of n. Maybe I'll do two loop space just so I can draw it out very explicitly. So the two loop space of n of Y, which is the loops of Y, where loop space of Y, remember to take a loop space, I need a base point. What base point should I use? Well, just a constant loop. So loop Y is naturally a base space. So I can sort of view it in two different ways. I can kind of view it as like maps of 0, 1 into maps of 0, 1 of Y, and I should like indicate like map prime to indicate that there's some sort of base point condition happening. And sort of if you're like very tensor homojunction brain, you might really want to write this as like some sort of map prime of 0, 1 squared into Y, like 0, 1 times 0, 1 Y. Because like sort of the definition of loop space, if I do loop space twice, is something like this. But you know, your brain might really hope that you can write something like this. And this is sort of a concrete illustration of the fact that E1 tends to E1 in place of work with the E2. And what do I mean by that? Well, loop space 2, modeled in this way, has a natural action of the E2 opera. So this space has a natural action of the E2 opera. So how do I compose two different maps from 0, 1 squared into Y? Well, it's just sort of like loops. I find two different ways of putting those maps inside a square, and then I just do both of them, right? So it's exactly the same as the composition of loops. So in a natural way, this loop 2 space is an E2 algebra. But it's also got two different E1 algebra structures. Because how else could I compose two things? Well, I could think about sort of putting my first, like I could sort of think about composing the two loops by composing them in this first time and then composing them in this second time. So somehow this loop 2 space, both it's an E2 algebra because of this description of the loop space, but it's also an E1 tensor E1 algebra that has these two E1 actions. And sort of if you do a lot of algebraic topology, you'll know that there's this like very famous Ekman-Hiltman argument, which whenever you have some object and you have two different operations on it that are compatible, by some miracle, those two operations are both the same operation and they're commutative. And something sort of similar happens here. So if you actually want to prove Dunn additivity, it's basically just a very hard Ekman-Hiltman argument, where you show that these two different E1 actions are basically the same action. And in fact, knowing that they're both sort of compatible lets you infer some sort of commutativity. And these EN algebras, we should think of them as in the same way that this associative algebra encodes more and more sort of associativity conditions. These EN algebras, one way of thinking about them is they encode more and more homotopy coherent commutativity conditions. And so just like the Ekman-Hiltman argument says that two different operations combine to give you one commutative operation, here it's saying that if I have like two kind of commutative operations, I can upgrade that to some sort of higher homotopy coherent commutativity. And it literally is like the proof boils down to an Ekman-Hiltman argument. It just takes a long long time to understand why that Ekman-Hilton argument actually applies to the card. So fundamentally, this Dunn additivity, it really is just sort of a special case of the Ekman-Hilton argument. So that's sort of the fundamental idea behind it.
I don't understand how many pages are taken up with this.
But I also don't know if that is like the most efficient way, or if he's doing other
1%
things.
of the book.
Yeah, so like, it's a very tiny fraction.
No, that's huge. 1%, I mean, like 1% of the US economy is. That's huge.
And so now, great. And so now to sort of justify the remark I made that EN algebras can be viewed as higher and higher commutativity conditions, I think I want to end the first half of the talk by defining E infinity algebra, like by defining the E infinity operad and explaining why that operad is the same as this sort of com operad of commutative modules that we had defined earlier. So it's a good word to erase. Why not? So the E infinity operad is just defined as sort of an operatic colimit. So the E infinity operad is the colimit of the EK operads over all the Ks. And actually trying to get like models of the spaces of like n-ary operations on an E infinity operad is kind of hard because you need to think a homotopy colimit of the spaces representing n-ary operations of EK operads. And like homotopy colimits are sort of a little like big for me to think of. So explicitly describing this is a little bit tricky.
What are the inner operations are just attractive. Right, I mean, the commutative operads is like, it's literally like, there's.
Well, it's not like even for an E1 algebra, they're not contractible because
No, that's saying when you go to E infinity.
Oh, yeah. So this is sort of why, so for E infinity, it will be contractible and sort of, that's actually why it's the same as this comma, as this sort of comma object. So E infinity,
Just for an idiot like me, colim in this case, you're limiting among maps that could point in as k increases or as k decreases, which is the one that we're limiting over. Is it
increases.
Okay,
Is it clear that EK maps to EK plus 1?
Oh, yeah, so EK, just sort of EK plus 1. So this sort of map comes from, basically I can multiply everything here by like another copy of 0, 1. And so if I have like an embedding of some, if I have like sort of an embedding of two things into the line, I can sort of multiply this whole picture by 0, 1, and then get a mapping of two squares into a bigger square.
Right.
Yeah, so that's sort of where I'm getting these maps from. Thanks. Yeah, and so now I want to talk about, I guess, so what Justin mentioned is that in the end, all these sort of operation spaces are contractible. And so this is sort of the kind of tricky thing to prove. And it results. So it results from sort of the following fact, which is that, so if we model the EK algebra using these configuration spaces. So I say I have like the configuration of n points in 0, 1. Okay, the claim, this is k minus 1 connected. So k minus 1 connected means it has trivial homotopy groups past k minus 1. So we saw this, hopefully I didn't erase the picture. We saw this with this explicit example here. So here we're looking at the sort of k equals 1 case, and this, as sort of just remarked, was homotopy equivalent to just 2 points. So it has like a non-trivial pi naught, but pi 1, pi 2, pi 3, all of those are trivial. So this is like a 0 connective space. And it turns out the configuration of n points in 0, 1k is k minus 1 connective. And this is sort of like, it's not the easiest thing, but you can put this as like an exercise on like an algebraic topology midterm for like a first year grad course, and probably half the class will get it. So like it's not, so it's not like the easiest thing in the world, but this is like some kind of more or less explicit computation that one can do. And Larry does it. So for a little happy face. And so if I take the configuration of sort of n points in 0, 1k, that's k minus 1 connective. And so when I take some sort of homotopy colimit over all the k's, the kind of level of connectivity is going to get higher and higher and higher. And so in the end, all the spaces of E infinity are going to be contractible. And because all those spaces of E infinity are going to be contractible, it's going to end up being the case that E infinity is isomorphic to that comms operator that just identified. AKA, so an algebra over the infinity operator is the same thing as like an algebra over the comm operator, which you should think of as like commutative modeling. So this sort of, maybe gives you some faith when I say that like EK algebras encode more and more homotropic covariance conditions under commutativity. This is sort of one justification for it. When I go all the way to infinity, I get like exactly super duper commutative operations. Right. And so I think now to end with, I want to actually maybe we should take the break now. Maybe now would be a good time to take the break.
Any questions before break
Yeah, so any questions before break?
from Zoom? All right.
Okay, great. Yeah. All right, okay, so now I want to, so last time we were thinking about this definition of the algebra is a functor on these sort of open sets with some sort of maps like this. And actually, to make things fit with the rest of the talk a little bit better, this is equivalent to sort of the following. Instead of looking at open subsets of 0, 1 to the k, I can look at open subsets of r to the k, isomorphic to this. And this doesn't really change much because O1 to the k are the same. So
Happens once a talk, don't worry.
So I want to recall now the definition of a Kosheav. So a Kosheav on C. So if I have an infinity category C and a topological space, I can talk about sheaves on that topological space valued in that infinity category. So a Kosheav on C is a sheaf on C, aka like all the sheaf axioms sort of hold for C up, which you can think of like sheaf axioms or some series of limits, just turn those into colimits. And then that's how you get like the Kosheav. So this is sort of a Kosheav. So Kosheav on C is just a sheaf on C up. And the reason I'm introducing this term is because the following theorem, I think it's sort of Duality, but only in the sense that like no one else would have ever needed this before. Which is that, so if I have an EN algebra A, like on that top one, then A can be extended to a Kosheav on the space ran RK. Oh wait, sorry, I'm using K and N. So maybe I should be consistent because they're supposed to be equal. So K algebra on ran RK. So what is ran RK? So ran RK is the set of configurations of any finite set of any cardinality. And you can imagine, how do I topologize this? Well, I can even sort of metricize it if I have like two different if I have two different finite sets of points. What I can do is I can sort of look at for each point the sort of shortest distance from a point in here to a point in the other set, and then look at the longest of those distances. And in that way, I can get like a metric defined on like configurations of sets of points on RK. And if I have, so A can be extended to a Kosheav on ran RK, call it to a Kosheav with the FA, so that, and what do I mean can be extended to? Well, really what I mean is that if U1 through UK are sort of disjoint, just like they are there, if they're sort of disjoint, then FA of ran of U1 through UK. So what does ran of U1 through UK mean? Well, it means the open subset of ran, where consisting of configurations of K points. Oh, sorry, I should use, well, this letter should be different. This letter should be like J. Got lots of indices all the same. So this should be configurations of J points in RK, so that the first point lies in U1 and the last point lies in UJ. And this, so sort of the sort of compatibility between FA and A, what this ought to be sort of tensor product of A on each of those. So sort of Fleury proved that you can always extend an EK algebra to sort of a Kosheav on RAND RK that has sort of this compatibility condition. So not all Kosheavs arise this way, but it will turn out that a very important Kosheav that Fleury and Gates-Corey consider will arise this way for the case of K equals 2. So, okay. And maybe I'll make sort of a comment. We were defining EK algebras. You can actually define EM algebras for any manifold M in sort of a similar way of like looking at like n-area operations on EM are just configurations of points in M. And there's a similar theorem that like if you have an algebra for the EM operad, then it can be extended to a Kosheav on random M. So if you want to like state sort of Poincare, if you want to state all these results in like the maximum generality, you should define these EM algebras for like arbitrary manifolds, but I think we're happy with RK.
What does it mean random U1?
Oh yeah, sorry. So this is sort of an open. If you like, you can think this is literally just the product of it. So these are a bunch of disjoint open sets. So their product automatically embeds in RAND space as sort of the configurations of J points, where the first point is from U1, the second is from U2, the Jth point is from UJ.
So like find like J points. Like the round space usually is all finite.
Yeah, oh yeah. So this is J is arbitrary. So RAND space is the collection of configurations of any sort of finite set of points you want. And here J is arbitrary. So there are some cases like, so here I'm saying like when I have the configuration of J points and I look at the sort of subset of the configuration of J point, like this is an open subset of RAND space. You're exactly right that this open subset only happens to contain points of RAND space corresponding to cardinality J. But here J is sort of variable. J can be anything. And so these open sets do form a basis for the topology on RAND RK, or maybe a sub-basis. I forget if the intersection is still of this form. So these sort of see the entire space RAND RK, because I can let J vary, and it's crucial that J varies. Yeah.
So you can find EM algebra for any algebra. What is like an ES1 algebra?
So an ES1 algebra,
E1 algebra or ER?
yeah, so for M a manifold, EM is an operad whose sort of K area operations are configurations of K points on M. And so algebras for that operad, they become sort of similar conditions to this, except instead of my open sets homeomorphic to disks being subsets of RK, I take them as subsets of my manifold.
I guess I was wondering, so like when M is the real line, it's the associative algebra.
Yeah, so when M is the real line, this is the same thing as an E1 algebra.
Right, so when M is a circle.
When M is a circle, I don't know if there's any simpler description other than that. Maybe someone here knows it, but off the top of my head, I don't know of any simpler description. Yeah, in fact, for any space that's not Rn, I don't know of any simpler description of these EM algebras, but also I just never really, like the only context in which I know about these operads is to state non-abelian Poincare duality. I've never really thought about their algebras separately. So this is sort of a theorem on Kosheaves on RAND space, and right now it's sort of like that's a bit wild. Like why we have Kosheaves and RAND space appearing. So I'm going to talk a little bit about non-abelian Poincare duality, which is a little bit besides the point, but it's going to sort of circle back to what we're doing here. So what's sort of some natural example of a Kosheav? So the thing that first got me into infinity categories in the first place is because I really wanted to understand the following sort of proof of Poincare duality. So suppose I have like an oriented manifold. So suppose I have an oriented manifold M, right? So Poincare duality tells me that compactly supported cohomology of M should be isomorphic to homology, maybe it's an N manifold, to homology, sort of like in the opposite degree. This is just Poincare duality. And here's like in a just world how we could prove Poincare duality. So Poincare duality in the case of M is like Rn, it's just a computation. Like sort of in your first course in algebra topology, probably you'll have to just compute both of these explicitly and see they're the same. And maybe like when you take a course in differential topology and learn about like de Rham integration, you'll find that in the case where like M is where M is oriented, there's sort of natural functorial maps from like for any open subset U of M, there's natural functorial maps. So there's natural functorial maps between them. And so sort of the ideal way that a proof of Poincare duality could go is if HC of the open subset and H and homology of an open subset were both sort of sheaves on it. Because then the fact that I can sort of functorially define a map here using like integration, then the fact that like I could define a map here, that would be like A-okay. That would like give a morphism of sheaves, and the fact that it's true, the fact that Poincare duality is true for like Rn would then imply, since you can check an isomorphism of sheaves locally, that these are in fact the same sheaf. And so when I evaluate the global sections, I get the same answer. So that's sort of how Poincare duality would be proven in an adjusted world, but it ends up being kind of hard. So there are a number of sort of problems with that template. The first problem is that these compactly supported cohomology and homology don't really behave like sheaves as much as they behave like Kosheaves. And the second sort of problem is that really their homology and cohomology are really, really bad. And what one should do is look at this sort of compactly supported chain complex. So I can define like a cosheave. I can define two cosheaves on M. One associates U to the sort of compactly supported cochain complex on U, and one sends U to sort of this chain complex on U. So it turns out that these two things are cosheaves. And I won't go through the full proof, but it basically boils down to the fact that the Meyer-Vittorius axiom holds. So yeah, like basically boils down to the Meyer-Vittorius axiom holds, because when I have sort of like a finite cover, like U union V is covered by U and V, if I formulate the Cauchy axiom there, it basically boils down to sort of this Meyer-Vittorius long exact sequence in homology for U and V in terms of homology of U and V. So morally, the Meyer-Vittorius sequence tells you that these two. So I have these two Cauchys. And Cauchys have basically the same sort of locality properties. And so now we can get like a perfectly nice proof of Poincare duality.
So just to make sure, the Meyer-Vittorius argument is also sort of saying that the map FU to FU intersection B to FU to FB to FU union B, the sort of square of that kind, is a push-out square, right?
Exactly. Yeah. So the Meyer-Vittorius argument is saying that that's exactly a push-out square. And so the reason,
So homotopy push-out square.
yeah. So right now I'm in this sort of infinity category of chain complexes. And so really, when I say like it's a push-out square, I really mean some condition on quasi-isomorphisms, which can be checked as a homological thing. And so if I think about how to check that homological thing, well, I basically need to check that the Meyer-Vittorius long exact sequence is an exact sequence. So it's not like, it's not exactly this. You have to be a little bit careful. And in the end, this is a tiny bit stronger than actual Meyer-Vittorius. But that's more of an artifact of how it's usually stated. And if you go through any proof of Meyer-Vittorius in any algebraic topology textbook ever, it will really prove this push-out square in this sort of infinity category of chain complexes, just without maybe recognizing that it does.
I see, because the explicit homotopy gets constructed or something.
Exactly.
I see.
So sort of like the actual Meyer-Vittorius long exact sequence isn't quite enough because you don't know where these sequence comes from. But if you think about any proof of it, the proof will show that it actually comes from something witnessing that this is a push-out square. In this sort of. So we have these two Cauchys. And so now I can get like a very quick proof, which is what we'll call it. So I have this sort of compactly supported cochain complex on M, which sort of by the Cauchy axiom is quasi-isomorphic to this sort of colimit over all the U and M, which are sort of U isomorphic to K of I guess C star U. So I have this sort of, this just follows from the fact that this is a Cauchy in the same way that like a similar statement would follow from if this was a sheet. But since M is oriented, I can get some sort of morphism of these two sheets. And actually, that's the only place where I use the fact that M is oriented, because I always have like just random maps from each individual U. but I need that M is oriented to sort of pick them in a consistent way to get like sort of a functor, like a morphism of Kosheaves instead of just morphisms for each individual U. So this is then homotopy equivalent. Or I guess maybe I'll say this maps into the colimit of U contained in M, U homeomorphic to R1, a sort of homology complex. But for subsets isomorphic to Rn, just by direct computation, you can see this is quasi-isomorphism.
Also, side question, this proof in its explicitness, is this, it's outlined in Murray's lecture notes, but does this appear in higher algebra or higher calculus theory or?
So it does appear in higher algebra, although the proof in higher algebra is of a slightly more general statement than in the lecture notes. And so it might be a little bit hard to go from the higher algebra statement to the lecture notes statement and to what I'm stating.
I see.
And this then is sort of in the exact same way isomorphic to the chain complex. So then I have some sort of big thing of equivalences, but saying that these are sort of saying that these are equivalent objects, these two complexes are equivalent objects in this sort of infinity category of chain complexes is exactly the same thing as saying that they have isomorphic homologies. So the compactly supported cohomology, which is the homology of this chain complex, is exactly the same as the homology, as the singular homology, which is the homology of this chain. And so this is sort of one quick way of getting a proof of Poincare duality. Although if you think about it, this is actually literally the exact same proof of Poincare duality that shows up in a book like Hatcher. Because what does Hatcher do? Well, he uses the Meyer-Vitorius axiom to establish things of this nature, and then he uses it for RK to establish things of that nature. And actually, as far as I can know, as far as I am aware historically, maybe one of the driving points of compactly supported cohomology was to make this sort of inductive proof of Poincare duality easier to formalize. So then this was sort of Poincare duality. Now, how do we make this sort of non-abelian? For this, I guess we'll introduce sort of analogs of compactly supported cohomology and homology in this sort of non-abelian case. So what are they? Well, in sort of Poincare duality, you start with an abelian group A, your sort of coefficients. You look at cohomology with coefficients in A. And you look at homology with coefficients in A. And the sort of Poincare duality, the sort of non-abelian version of this is you start with a pointed homological space. Y. And it will turn out that these sort of cohomologies will end up corresponding to fundamental groups of compactly supported maps from M into Y. And what does compactly supported maps mean? Well, that's why we have to give Y a base point. So compactly supported means that outside of a compact set, this map is just the constant map sending everything to Y. So like you can think like a usual compactly supported map on R would be the case where this is R, 0. And now it's just instead of almost everything goes to 0, it's almost everything goes to 1.
So is that a subscript N, or is that a subscript 1?
Oh yeah, so this could be an N. I guess I was doing stars here, so maybe if I make
Probably the N.
so this cohomology sort of maps up with this N homotopy group. And then this part ends up being a little bit harder to formulate, and this is where Kosheaves on RAM is going to come in, is to make sense of homology in this sort of non-abelian way. So
Sorry, what's the analogy here? So in what sense is this the right side like a non-abelian version of the left side?
oh yeah. So maybe one way of thinking about what's happening is if Y is the classifying space of this abelian group A, then this is literally true. It's literally true that the compactly supported cohomology would be the fundamental groups of this compactly supported mapping space. So this is sort of what motivated Lurie to make this analogy, is viewing cohomology as sort of homotopy classes of maps into a classifying space. And if I
Is there a shift by 1 or?
maybe there is a shift by 1.
Yeah,
It's
maps.
I0.
Oh yeah, so okay, so probably there should be some shift by 1.
If I recall correctly, there might be a typo. Actually, these lecture notes, one of the rare.
Yeah, okay, yeah. So you're probably exactly right that I want some sort of shift by 1 to occur here. But yeah, so if I take Y to be the classifying space of A, then maybe up to some shift by 1.
Probably also 1 minus.
So some subscript there.
I'm sorry, I'm sorry.
There's like some subscript there, like up to some shift, which will make it map exact. Right, so
So we did, the y will be related to a, like it was the client, the y will be determined by whatever non-abelian way is.
yeah, so somehow the y, you should think of, like in the abelian case, y is the classifying space of A. And in the non-abelian case, y is just, that's just something. Although usually, like you're gonna want y to have some sort of connectivity properties.
It's gonna be the classifying space of a non.
Right.
Yeah, I think like in Larry's actual proof, probably y will be BG for non-abelian group G, when he's using this proof. So. Anyways, so I want to state now non-abelian Poincare duality. So what does non-abelian Poincare duality say? Oh. Non-abelian Poincare duality is sort of the following statement. Okay, well, Larry, there exists a Koszul hat. So what I'll do right now is I'm gonna fix a manifold M, maybe an M manifold, and I'm gonna fix a pointed space Y. And there's going to be a Koszul F on ran of my manifold M, such that F ran of U1 to Uj is how much of an equivalent to this sort of product of mapping spaces of exactly similar mappings from I to Y. Whenever the U1 and Uj are just any disjoint focus in M. So there's some Koszul F on random, so that if I look at it evaluated on this sort of basic open sets, random U1 through Uj, I get this product of these mapping spaces.
Koszul spaces,
It's what's this?
Koszul of spaces,
Oh, yeah, so it's a Koszul of spaces.
I would assume is it gonna be in like the homotopy coherent sense or kind of?
In like a homotopy sense. So here this is like an infinity category of spaces, and whenever I say Koszul, I made it in this sort of homotopy sense. Yeah. So this is sort of the statement of non-abelian Poincare duality. So there's a Koszul that sort of has this property. And so in what sense is this like viewed as non-abelian Poincare duality? Well, the idea is that what you will call it, the idea is that just like the sort of homology of M can be computed as this sort of co-limit of simple to understand things, the sort of sheaf condition, the Koszul condition on M will tell us that map C from M into Y, this sort of space, just like the compactly supported cohomology of Y, should somehow be homotopy equivalent to a limit over U of I guess like U1. We'll say like a limit over U ranging over U is marked Rn of this Koszul F of like ran U. We now use as more to a disjoint union. And I guess F of ran U would just be C. Why? Okay, so this sort of Koszul F is kind of like our Koszul of compactly supported cohomology from before. And so this is sort of, and so Larry considers this like sort of a non-abelian version of this. And the reason that I sort of want to introduce this is because earlier I told you a different way of getting Koszul. So here this is saying that there's some Koszul of this having this property. Here I define Koszul with a very similar sort of thing. So I have Kosheaves on the Rand space of RK associated to an EK algebra that can have this nice property. So sort of some relationship between like non-abelian Poincare duality and sort of this sort of thing, is you can ask, does this Kosheav sort of arise as the Kosheav attached to an EK algorithm? And this is sort of some interesting question, and I think kind of another question that I kind of want to address is now related a bit to Verdier duality. So Verdier duality is sort of something from classical algebraic geometry. And Larry sort of states it in a way which maybe looks a little bit unfamiliar to classical algebraic geometry, which is that Kosheaves on X, aka sheaves on CL, so this is the category of Kosheaves, are equivalent to the opposite of the category of sheaves. So this is Verdier duality for space X. Kosheaves are equivalent to sort of the opposite of the category of sheaves.
Sorry, I'm very confused. So we're talking about sheaves on X, right? So
Yeah.
they're functors on the category of open subsets of X, right? C is the values of the sheaves?
Yeah, so sheaves valued in C.
I see.
And the open set category is those isomorphic disjoint because of balls or just all open sets?
The normal.
Oh,
So all the open sets. Although in the case where X is a manifold, you could restrict to that category, and since like disjoint unions of balls form a basis for the topology of the manifold, you could restrict to that category without changing the sheet.
would understanding some kind of local model and for singularities, kind of appear in algebraic geometry, could be like Verdier duality for singular things, the perverse duality or something like that. Is there a way of seeing something like that from this perspective, or?
Maybe, but I don't know.
I see, okay, sorry, that's a bit of a loose question.
Sorry, I'm still confused how this could, this statement has like any content to it, right? Because like normally Verdier duality involves like kind of term-wise dualizing.
I could tell you how we can recover normal Verdier duality from this,
Great,
and then
great,
maybe
yeah.
you could,
Yeah,
maybe you would
okay,
be happier for that.
great.
So let's see. See the category of vector spaces over K, and maybe I'll make them just vector spaces over K. So there's a map from C to C up, given by taking the dual of the vector space. This is some sort of contrary thing.
Sorry, about that, by that you mean the ordinary category viewed as an infinity category?
Yeah, sorry, so
Okay.
to me, all categories are infinity categories. So this is a map from Kosheaves. I guess maybe I have to write it C
Oh,
off C.
wait, sorry, so it's Koszul there, not sheaves?
So sheaves on C off or Kosheaves on C.
It's not sheaves on CF, but sheaves valued in CF, right?
Or sorry, when I say sheaves on C off, I mean like sheaves valued in C. Sorry, I do mean like sheaves on X valued in C. Like this is what I mean.
So it has nothing to do with Koszul's, right? Because that would be on the opposite of the open subsets. of X or whatever.
Oh, yeah,
Sheaves,
yeah,
you see what I
yeah.
mean? It's a different opposite.
Yeah, okay, sorry, yeah.
What?
Okay, so this is sheaves on C up, and then opposite category of sheaves.
Yeah, is it not
Wait,
trivial?
actually, yeah,
That
never
that
mind.
off and off, you can double op, right? Functors like functors from X to Y off, or functors from X off to Y or something.
I see. Yeah, that's what you're saying. Okay, got it. Right, functors from open subsets of X into C op is the same as functors from the opposite category of.
Yeah, okay, so this is
C. That is actually good.
Okay,
Okay,
Great.
great. And this is what I thought.
yeah, Koszul's
So,
valued in
this is
C
Kosheaves.
or
Yeah, yeah.
she's
So this is
valued.
sort of, so variability is expressing that Kosheaves is true in two sense. Kosheaves are like co of sheaves, or like they're co of sheaves in this other sense. So like, how do I recover like maybe classical Verdier duality in algebraic geometry? Well, if I have vector spaces on K, I can take duals, so I get a map from here to here. But maybe if I restrict myself to finite dimensional vector spaces, this will end up being an equivalence of categories, just because this is an equivalence of categories. And so now it's saying that there's some sort of equivalence from this category to its opposite. And that equivalence, that contravariant equivalence, is precisely the usual Verdier duality. So this like is sort of a non-trivial theorem because it like in this it recovers normal Verdier. As we're sort of used to. So then this is Verdier duality. And maybe sort of I think I have about
So
like
this is probably probably true only for X locally compact, right?
yeah, so actually, sorry, so maybe I should say this X locally compact. And maybe
Not true for Ron space.
yeah, so maybe I'll say like the way one proves this is actually one so earlier Dunn sort of asked a question about what open subset category I was using, and I remarked that if X is manifold, you might as well just take the open subset category to be open subsets like isomorphic to Rn, just because there's one of agents. So the way this is proved is you look at sort of, you can view sheaves by restricting them to their sort of compact, like I guess pre-compact opens. And if X is locally compact, that doesn't lose any information because X has enough compact sets that that's actually a basis for the topology. And actually, so in the proof, I guess for X not locally compact, Larry proves a slightly different theorem, which is that sheaves sort of on the site of pre-compact opens of X have this property. But if X is locally compact, then the site of pre-compact opens is exactly the same as the site of like all opens, at least when you're taking sheaves. Like an equivalent site in the case of X locally, one stands to the other.
Space for this. The pre-compact.
I think the better way to think about it is for Ron space is like a filtered union of locally compact spaces. And so Kosheaves on Ron space will be equivalent to like the limit of categories of sheaves on those locally compact, but under shrink pullback functors as opposed to star pullback functors. So he literally calls these like shrink sheaves. Okay. So it's actually more like the category of B modules on space in that sense. Yeah. So in this way in particular, like if you're allergic to Kosheaves, like maybe I am, like you can just ignore them because like for locally compact spaces, they're the same thing as sheaves. And then for these things that are built out of like infinitely many locally compact spaces, you can say some words about it. Shrink pullbacks. It's like I can support it.
Yeah. So maybe I'll sort of say that a little bit louder. So what Aaron just mentioned and what Justin just mentioned was that Kosheaves on like sort of a locally compact space are basically the same as sheaves, because if I have any sheaf, like say the sheaf of cochain complexes, I can take its compactly supported sections and I get a cosheaf. And so if you have a compactly supported, like if you have a locally compact space, sorry, then it turns out that every cosheaf basically arises from this construction. I take an ordinary sheaf and I look at its compactly supported section.
It's equivalent, so that's the right part. Yeah.
It's not like it's not an obvious fact, but it is sort of a fact. So I kind of want to draw a little picture. So maybe I'll kind of draw this diagram over here. So we have some sort of category of Kosheaves on land of RK, which we already saw. If I have sort of an EK, I'll call an EK space, an EK algebra in the category of spaces. So here we saw if I have sort of an EK space, I can get a Kosheaf on ran RK, like a Kosheaf valued in spaces. Although maybe I can just say Kosheaf on C and then EM algebra, or EK algebra on C. And here, there's this sort of Verdier duality. With sheaves on random. Okay. And in exactly the same way that EK algebras on C give rise to Kosheaves, EK co-algebras, which if I remember correctly, I think Justin defined.
No, I didn't define co-algebras. I weighed my hands.
So co-algebras are sort of defined in exactly the same way as Kosheaves, which is namely a co-algebra is just an algebra on C up. So co-algebras give sheaves, and this is basically because of the same construction, because what is like algebras give Kosheaves, Kosheaves are sheaves on C up. So somehow algebras on C up, aka co-algebras, should give co-Kosheaves, sheaves. So you might ask sort of another question, which is there some direct way of seeing like what Verdier duality is doing on the level of EK algebra? So if I take my EK algebra, turn it into a Kosheaf, Verdier duality sort of, like I guess we're right that this random space Verdier duality doesn't quite hold. So like this thing here doesn't actually exist. But we can ask, is there some sort of analogy to Verdier duality occurring at the level of EK algebra? And this is sort of like a crucial ingredient to the proof of the atomic hour number formula, because sort of like Justin was saying earlier, they can't really do Verdier duality on random spaces, but they really want to. So Larry was very, very clever, and he found a way of doing Verdier duality down here. Like he found some sort of operation analogous to Verdier duality down here. And then he could pretend he had Verdier duality because all his Kosheaves had turned out arose from certain E2 algebra. Or at least the Kosheav he wanted to apply Verdier duality to arose from a certain E2 algebra. And so even though he doesn't actually have Verdier duality down here, Larry was very clever and figured out a way to make it work by finding an operation here. And that operation is called Koszul duality. And I think probably we'll end by giving the kind of long definition of what the hell Koszul duality is. So the sort of classical way that Koszul duality comes up is actually so Peter May told me it was due to Peter May. Peter May also said lots of things are due to Peter May, so maybe we so I'm gonna say it's due to Peter May, but I'm not sure how true this is.
That was typical.
You prove like the bar complex is a algebra or something like this, that sounds.
Yes, I think this is somewhere in the geometry of iterated loop spaces.
Yeah.
So Peter May loves the bar construction, so at least this is like a believable statement what I'm about to do. So
But I take it it's not due to Koszul?
somehow no.
True to
To be honest, I really don't know what the connection is with Koszul.
There's a huge abuse of terminology here, but it is explained in this paper by Ginsburg and Ronoff. There's like a precise relation between like the bar thing and then the kind of quadratic Koszul thing. So yeah,
Okay.
maybe I'll explain it.
Okay.
The bar complex is Miller, right? Well, bar complex.
So Peter May asks, suppose X comma X is an n-connective space. And suppose you know omega nx with its En algebra structure. So you know this not just as sort of a topological space, but as an En space, but you've forgotten X. Can you recover the homotopy type of X? AKA, can you recover X up to weak homotopy equivalence? And this is something Peter May was like very, very interested in. And he invented most of the theory of operads to answer this question and questions of a similar nature. And so how do you do that? Well, for n equals 1, well, a one connected thing is basically just a fundamental. So a one connected thing is basically just a fundamental group. And so Peter May thought, how do you get it? Well, remember, omega x is not like on the nose topological group, it's basically a topological group. So you can take its classifying space. And this is sort of the idea that Peter May had, is you can reconstruct X as the classifying space of this. And then this should sort of reconstruct the homotopy type of X in the case when X is one connected. So, and what precisely like sort of is a bar construction of omega X? Well, so omega X has this sort of E1 algebra. Is an augmented E1 algebra. So you sort of have a natural map down to the point, which allows me to form a sort of tensor product of the point times the point over omega x. Why? Well, because an augmentation actually gives the point the structure of an omega x algebra. How? Well, remember, actually that part is not on Zoom. Maybe I'll just draw.
Oh, we can probably capture. We can probably. Okay.
So if I have an augmentation like omega x to point, well, omega x is the same as point tensor omega x. And what is a map point tensor omega x to point? Well, that's just like a right algebra structure of omega x on the point, right? That's just a way of multiplying things in the point by elements of this group. And similarly, the point also sort of has the left structure, has sort of like a left structure as an omega x algebra. And if I have omega x acting on something on the left and acting on something on the right, I can take this sort of tensor product of like here it acts on the right, here it acts on the left. And so how do I take this tensor product? Well, if you know how to take sort of absolute tensor products, you sort of take the absolute tensor product, and then you have two different maps from this absolute tensor product here. So what are the two different maps? Well, the thing in omega x, you can either make it act on the left, or you can make it act on the right. And if I take the co-equalizer of these two maps, I can define this sort of tensor product over omega x when I have like a left action of it on something and a right action of it on something else. So this sort of weird tensor product is precisely the bar construction. Or I guess it's called the double bar construction, but this, the B here, is precisely this little tensor product. It's precisely this little tensor product. And I'm not going to go into the full story of sort of how Peter solved this question, but the reason I wanted to give it is because it motivates the definition of Koszul duality, which is Peter sort of solved this question. He had to figure out like how to generalize the classifying space function, and he realized that actually this is like a pretty good replacement for the classifying space functor, even in the case when omega nx is not, or like when n is bigger than 1. And this leads to the idea of Koszul duality.
Wait, is that not the definition of classifying space?
Oh, this is for like e for n equals 1.
Right, right,
yeah.
okay.
It's just for like n bigger than 1, it's a little bit different. For n bigger than 1, this side no longer makes sense, but this side still makes sense. And this is sort of the observation that Peter had to solve this problem, is he rewrote this in this way, but this side still makes sense. Oh, what? Yeah. So like Kevin said, we're now about to iterate this plot. So an augmented algebra, recall, is just like an algebra for an operad with a map to this sort of, I guess, whatever your sort of unit object. And when I'm working in spaces, my unit object is the point. But if I'm working in some sort of general monoidal category C, I think actually this can all be done even without the symmetric condition, but I don't know if that's true, so I'm going to say symmetric monoidal category C. In a symmetric monoidal category C, I really do, yeah, like I have just some arbitrary unit object 1. And so what the bar construction is we're taking maybe E1 algebras with an augmentation in a category C and turning them into sort of augmented coalgebras. So an augmented coalgebra, which is sort of like a coalgebra with augmentation. And the bar construction is exactly that sort of double tensor product we did there. So what's the bar construction way? It's 1 tensor over A with 1, sort of in the exact same sense that I meant this tensor product there before. So the augmentation gives a left and right action of A on 1, and so I can form this sort of tensor product. And this is called the bar construction. And remember, coalgebras on C are the same thing as algebras on C op. So this is sort of the same thing. It's co-augmented E1 elements on C op. And now we're going to invoke Dunn additivity. To sort of iterate this and see what happens. So the idea to solve the problem is to do exactly what Kevin said, and just iterate the bar construction over and over and over. And so now, if I have an EN algebra, maybe I'll do it in the case of 2, so I can write everything out very, very explicitly. So let's say I have an E2 algebra, A, in some sort of symmetric monoidal categories. So I have this E2 algebra. I can take the bar construction of A in the following way. So E2 algebras on C, these are the exact same thing as E1 algebras on the category of E1 algebras on C. And so I can apply the bar construction to A by viewing it as an E1 algebra on the category of E1 algebras. And so in the end, this would be an instance of now an E1 algebra on an opposite of E1 algebras on C. So now I have sort of this little thing. So now I have this sort of thing. So want to do that. So if you take bar of A. And so bar of A, well, now this is going to be sort of an E1 algebra.
Bar, elephant. Children's story.
Bars.
Okay.
So if I iterate the bar construction, so if I do bar of bar. So now this is an E1 algebra. So bar of A is like an E1 algebra for C, some kind of really wonky category. So now this is an E1 algebra of an E1 algebra on C. And I think I take the off again. So I should be all good.
Should be two ops probably, right? It's like C op and then op on the outside.
Oh, yeah. So off. Oh, yeah. Okay. This is exactly what I want. Good. Okay. And this ends up being equivalent to E2 algebras on C op. And so when I do the bar construction twice, I take an E2 algebra on C and I produce an E2 algebra on C op. Or in other words, the iterated bar construction is precisely some sort of construction that takes augmented E2 algebras and spits out augmented E2 co-algebras. So this is sort of the twofold bar construction. And if you like formulate this as some sort of inductive proof, you can see that the k-fold bar construction will take an augmented EK algebra and spit out an augmented EK co-algebra. So now I can define Koszul duality. So Koszul duality is just sort of the ordinary dual. It's just sort of the ordinary dual of this co-algebra. So let's recall the definition of the duals. The dual of the X in a symmetric monodal infinity category C is some sort of object X V obeying a universal property that the mapping space in C of any test object rho in C to any test object rho in C into X dual should be the same sort of by the tensor homojuncture as this. So this is sort of how I define duals, is objects obeying this sort of universal property. And now I can define, so if I take an E and L, and maybe I'll just say an E2 algebra A, well, I can form bar 2 of A. And this is some sort of E2 co-algebra. And I can take its dual. And it will turn out that duals are a bit of a contravariant thing. And so if you take a co-algebra and dualize it, then the result will be an E2 algebra. So this will be another E2 algebra. And this will be called the Koszul dual. Koszul dual of A. So this will be called the Koszul dual of A.
Sorry. Isn't it the other way? Isn't the dual of a co-algebra an algebra, but not inversely in general? Yeah. Is that right? So like, if you think about like, say, take C to be all vector spaces, and take like an infinite vector space, right? If I start with a co-algebra and dualize it, then I get an algebra. But if I start with an algebra and dualize it, the kind of arrow goes in the wrong direction. Like the tensor product of the duals maps to the dual of the tensor product, but it's not an isomorphic arrow, right?
Yeah, yeah.
So it's, I think it's, yeah, it's going to be a problem with that.
Kevin, what if I did wrong? Because I should just take the dual of the iterated bar to get the Koszul dual, right? So what do I actually do?
And it may be that you can only produce an algebra that's not like if it's kind of has.
So it might be okay. So it might be the case that like I'm secretly assuming some sort of finite dimensionality.
Yeah, I think that's the only case in which you'll get like a verbal algebra.
Okay. So maybe we'll just sort of say that. So I'm assuming some sort of finite dimensionality condition so that the dual of this co-algebra is actually a genuine algebra. Okay, thank you for catching that. Great. So then this is sort of the Koszul dual, right? And this Koszul dual thing is precisely,
Sorry, maybe it's not so bad, because like very often you'll have a grading around with kind of finite dimensional grading. Which is why this like works so often. Finite dimensional algebras are kind of rare, but like things with finite dimensional grading. This type of thing. Just like you see a lot of gradings for stuff.
okay, yeah, great. So then this Koszul dual of A is exactly the sort of thing we need to fill in to sort of get an analogy of Verdier. So this should, so somehow the sheaf associated to this should be like Verdier dual to the co-sheaf associated to A. Great. Okay, and this, I think this is sort of exactly what I want. And then, yeah, I think this is sort of exactly what I wanted. And so maybe actually, maybe I should say something a little bit more precise to end on. So give a sort of more precise theorem to end on as to explain why Koszul duality is sort of some sort of analog of Verdier duality. Let's take C, the infinity category of R modules for some like ring R. And let's take epsilon, sort of augmented EN algebra. So then I can define the augmentation ideal MA as, I guess, like I would call it the kernel of epsilon, but Jacob Larry calls it like the fiber of epsilon in this sort of super derived infinity category. And so MA is a non-unital EN algebra, which is exactly the same thing as an EN algebra, except there was some like condition of coherences, and before I would allow k equals 0 in that set, meaning I always had maps from 1 into A to V for any V, sort of picking out a unit. And non-unital just means I don't have those maps anymore, but I have all the other ones. So MA is a non-unital EN algebra. And if I look at the sort of Koszul associated to this non-unital EN algebra,
I think that is a bit like take a map of two algebras, two rings. And then
yeah, this is exactly like the kernel. Yeah, the kernel is
ideal, which is
yeah.
non-abelian.
Exactly, yeah. So that's sort of exactly the thing to think of. This is sort of Verdier dual, it's Koszul Verdier dual to F and B, where now B is the Koszul dual of A, and so this bar construction produces like augmented things, so I can get an augmentation ideal MB in the exact same way. And this is sort of the final theorem, is that if I take some sort of EN algebra, I look at it sort of with an augmentation, then the sort of non-unital, the Koszul associated to that augmentation ideal is Verdier dual to the sheaf associated to the augmentation ideal of the Koszul dual. And so this is, I think, what I want to end on. Yeah, so this is sort of what I want.
I think it was a false alarm by the way. Duality thing, because it's the dual of a coalgebra is an algebra. It's the other direction.
Oh, okay.
Fails, and so it's actually okay.
Okay, good. So I was in the good direction.
Because like if I have like a coalgebra C, right, like C dual tensor C dual maps to C tensor C dual, but it may not be in this place. So if C was a coalgebra, then you could.
Oh, okay.
So okay, it's all.
So the definition of Koszul dual is okay. Good. So great. So F of MA is Koszul dual to sort of is Verdier dual for this sort of Koszul dual. This holds whenever I'm in a nice case. And so the idea of sort of the Lurie proof, as far as I can understand it, is he really wants to take the Verdier dual symptoshi that arises from an E2 algebra, but he can't do that. And so Lurie's, I guess, maybe Gauge reached this point and was very, very sad. And then Lurie figured out this sort of trick about Koszul duality, and then you could make the argument work. It's everyone was happy. Great. So any questions?
Thank those people.
Any questions from Zoom?